Today we are going to learn about Hess's law. This is a very useful rule in chemistry that helps us calculate the enthalpy change of a reaction even if we can't measure it directly in the lab. So first I'm going to state or write the definition of Hess's law. So Hess's law states that if you can add two or more thermochemical equations, if you can add two or more thermochemical equations, then the sum of the enthalpy change for the individual reactions is the enthalpy change of the final reaction. So I'm going to write this down. The sum of the enthalpy change, delta H enthalpy change for the individual reactions or the step reactions, for the individual reactions is the enthalpy change for the final reaction. I'm gonna break this down and clarify it step by step. So the thermochemical equation and its enthalpy of a reaction are in general directly proportional. So let's learn the rules of Hess's law. So it means that whatever you do to the original reaction, it is directly reflected to its own delta H. So for example, here this is a given reaction of 2 magnesium reacting with oxygen to produce 2 magnesium oxide with an enthalpy change of negative 1204. Now, let's make some changes to this enthalpy or to this reaction. So for example, if you multiplied, let's say, this reaction by a certain coefficient, let's say you multiplied it by 2. So you're gonna multiply all the reactant and products of this equation by 2. So here you will have 4 mg, 1 times 2 equal 2O2 and 4 MgO. And just how you multiply the reactant and products by a coefficient, you will also multiply the enthalpy by that coefficient. So it's going to be negative 1204 multiplied by 2, so negative 2408 kilojoule. So if you multiply your equation by a coefficient, the delta H is also multiplied by this coefficient. Similarly, if you divided a reaction by a coefficient, so let's say we decided to divide this equation by 2. It means this over 2 over 2 over 2. So that's a 1 mg, half O2, and 1 MgO. What will be the new enthalpy? It will be the original one divided by the coefficient that you used. So it is negative divided by 2. And the answer is going to be minus 602 kilojoule. What if you reversed the original given equation? So this is the original one over here. What if I reversed it? This is the one. If we reversed it, what will the equation become? So this is the product, it becomes the reactant. So 2 MgO will produce 2 magnesium and 1 oxygen. So when you reverse an equation, you reverse the sign of delta H. So up it was negative 1204. Now it's going to become positive. And if the original one has a positive enthalpy change, it will become negative. Let's take another example. So suppose you have this equation with a given enthalpy. Let's see here, what did we do? The B is here on the other side and the O2 is on the other side. So apparently we reversed the given equation. That's one thing. But also, you can see that first you had 4, 3, 2. Now you have the B is 8. The O instead of 3, it's 6. And the B2O3, it's 4. So it seems that you reversed the given equation and you multiplied it by 2. So what will be the delta H? When I reverse, the negative becomes positive. And because you multiplied by 2, you need to multiply the enthalpy as well by 2. So your answer must be positive 5094 kilojoule. Now, moving on, now we're going to learn how to apply Hess's law when we have set of equations. So for example, I need to calculate the enthalpy of the reaction A to D. However, A to D seems difficult to happen. So we're going to do 3 other reactions. A to B with an enthalpy of delta H1, B to C with an enthalpy delta H2, and C to D with an enthalpy delta H3. If you look over here and you added those equations, you will see that B and B, they cancel out because they are not on the same side. One is product, one is reactant, so they cancel out. Same thing for the C, they cancel out. So we will remain with A to D, which is this one. And how did we reach A to D? We just added those 3 given equations. Therefore, this enthalpy here is going to be the sum of the enthalpies of the steps that led into this final equation. Now, as a result, I'm just going to, again, Hess's law is used to determine the total enthalpy of a system by imagining that each reaction is part of a series of reactions, each of which has a known delta H. Now, one more thing I'm going to do in this video tutorial, I'm going to give you examples to practice and solve to learn more about this Hess's law. So, here's in this one, we have a given overall reaction. And we are interested in finding the enthalpy of this reaction. So what's the way to do that? So first you need to know who's your target reaction. And you start looking for the reactants and the products of your target equation. Search for them in the given equations. So for example, XeF2, where is it in reaction 1 or in reaction 2? I found it over here. Now I ask myself, I need XeF2 to be a reactant. Is it a reactant? Is it on the reactant side in reaction 1? Then yes, it is. So it means that reaction 1, no changes. I'm going to keep it the same. I move on. I'm done with this. Now I look for F2. Where is F2? F2 is in reaction 1 and in reaction 2. In a case where you have an element found in more than one reaction, you better skip it because it's going to cause you headache and it might confuse you. So it's okay, skip it and check where to find XeF4. So, and F2, rest assured that F2 will be fixed automatically. So, let's now find where is XeF4. XeF4 is in the reaction 2. I need it as a product. Is it in the product side? Yes, it is. So again, reaction 2, nothing to be done to it. I'm not going to multiply. I'm not going to flip. I'm just going to keep it the same. Therefore, in Hess's law, always you need to add those steps of reaction. If a reaction is a multiple steps, you need to add them. So here, XeF2 adds up XeF2 adds up here. Now, xenon and xenon from both sides, they will cancel out. They don't add up, they will cancel out because one is a reactant and one is a product. Whereas 2F2 and 1F2, they cancel out, but they're not equal quantities. On one side, I have 2 in the reactant and I have 1 in the product. So they subtract with remaining 1 F2. You see? The F2, I need 1. So it got sorted out automatically. And this one here. You see this one? It's the target equation. I just got it back. How did I got it back? By adding these two reactions. Therefore, I'm gonna add these two values. And the enthalpy of this reaction is gonna be negative 139 kilojoule. Let's move on into more complicated examples. So, I have 3 equations, A, B, and C. And here is my target equation. I always tell my students, look for the compound one by one, search for it. B2H6, I found it in A. I need it to be a reactant. Is it here as a reactant? No, it's not. So we decide that we need to flip equation A. So you write A again. B2H6, so you flip it. So B2H6, I'm starting with this one, gives 2B and 3H2. And just like I explained previously, if you reverse a reaction, the delta H will be reversed, kilojoule per mole. I'm done with this. Now, let's find O2. This O2, I have it here and I have it here. It's gonna confuse me because it's found in B and C. So skip it. Check another molecule that's much easier than O2. Let's see B2O3. B2O3, I can find it over here. Now B2O3, I need it as a product. And in this one, it is coming as a product. So in C, I'm not gonna do anything. I'm just gonna keep it the same. So you write it again without any changes. 1.5 means a 3O2, 3/2 O2. And this is B2O3, solid gas. So I didn't do anything to it, so the delta H remains the same, kilojoule per mole. Now, the third one, I need to look for H2O. It's over here. It is a product. However, I need a 3 next to it. There is no 3. So I decide that all equation B, I need to multiply it by 3. So you're going to say 3H2 with 3 times half is a 3O2 and 3H2O. And for this one, again, you're going to multiply it by 3. So upon multiplying it by 3, you will get negative 858 kilojoule. Now, adding up these equations is a verification that you reached the target. So 3H2 and 3H2, one reactant, one product, they cancel out. 2B reactant and 2B product, also they cancel out. 3.5 plus 3.5 O2, they add up because they are on the same side. So that is 3O2. You see, O2 problem is solved. And these two remain in the equation. So again, I got back the target equation. And therefore, the enthalpy is the sum of all these values. So it's negative 36 and 1074 and 858. So the final answer is negative 2168 kilojoule. Again, one more example. Here's my target equation. That's my target. So that's my target. And I am given equation A, B, and C. So I'm gonna search for it. I found it over here. However, C4H10O, I need it as a reactant, not a product. So I decide to flip the A. So it's gonna be C4H10, I'll write it again, and I flip it. And if I reverse an equation, I need to reverse the sign of its own delta H. So this becomes positive 335 kilojoule per mole. Now C4H8, it's here. I need it as a product, it is a product. So B remains the same. H2O is over here. I need it as a product, it is a product. So I keep equation B and C, no changes, the same. So I'm gonna copy them all again. This remains negative 17. And this one as well, equation C, H2 gas and half O2, H2O gas with no changes on the enthalpy. Now, the last step, add them all. Half O2, look at it. Half O2 on the product side and half O2 on the reactant side, they cancel out. 4C in product and 4C in reactant, they cancel out. Now here I have 5 hydrogen on the product. But I do have 4 here and 1 here. And those, when they add up, they give me 5 H2. So here I have 5 H2 that will cancel out with this other 5 H2. And that's it, problem solved. I'm left out with C4H10 and C4H8 and H2O gas. So the final answer would be the sum of these values. So 335 minus 17 minus 242, and the final answer is 76 kilojoule per mole in applying Hess's law. So here's your target equation over here. That's the target. And I'm gonna name this equation A, B, and C. I need to look for each component. CLF, I find it in A. I need it as a reactant, so I decide that I need to flip equation A. Not just only that, I need to get rid of this 2, which means I need to divide all of equation A by 2. So it means this becomes half if it's divided by 2. This over 2 becomes 1, half, and half over here. So how will this reflect on delta H? Delta H that was negative becomes positive, and it must be divided by 2. So it's going to be 167.4 over 2. So the answer now is 83.7 kilojoule. So flip A and divide it by 2. I'm done. Now let's move on to F2. Where is F2? I can find F2 in equation C. I have it as a reactant, so it's okay, it's on the correct side. However, I need 1 F2, and here I have 2 F2. So I decide to divide equation C by 2. So divide by 2. This will reflect back on the delta H. So negative 181.7 over 2, it's going to be negative 90.85 kilojoule. I'm done with this. Now, let's look for ClF3. ClF3 is over here. It's in equation B. First of all, I need it to be a product. So I need to flip reaction B. Not just that, I need it 1, and here I have it 4. So I need to flip and divide by 4. So flip and divide by 4. So this one is going to become negative 682.8 divided by 4. over 4. So the answer is negative 170.7 kilojoule. And now the final enthalpy is by adding all of them. So it is 83.7 plus negative 170 plus negative 90. So 83.7 and 170.7 and 90.85. So the final answer is going to be negative 177.85 kilojoule. That's the final answer. Now, if you want to make sure that you got the original one, you can simply copy the new equation A. So I said we flip, so half O2 plus 1 CLF and half Cl2O and half F2O. The new B is going to be flip B and divide by 4. So it's going to be 3 over 2. I'm writing here F2O and half Cl2O and 1 O2, 4 over 4 is 1, and 1 ClF3. And in C, I just said divide C by 2. So it's going to be 1 F2, half O2, and 1 F2O. Let's add them up and see, do we get the original one? So here I have F2O half and 1. That's a 3 over 2 F2O. And on the other side, I have 3 over 2 F2O. So they cancel out. See, I don't have F2O here, so problem is solved. Now, I have half Cl2O a product and half Cl2O reactant. So my problem is solved. I got rid of Cl2O. I have half O2 and half O2. That means 1 O2. But on the other side, I have another 1 O2, so they cancel out. The only remaining substances is CLF, F2, and ClF3, and that's exactly what I need. F2, ClF, giving ClF3. Look, here's the target equation. I got it back with an enthalpy of negative 177.85 kilojoules.